Hello, my name is Nama and I will present our work NAN, Noise-Aware NERFs for burst denoising, a joint work with Tali Treibitz and Simon Korman from the University of Haifa. In limited light conditions, a single image will be very noisy, but multiple images taken with a tripod can be simply pixel-wise averaged to produce a decent-looking image. Without a tripod, however, the camera movements result in a blurred average. These camera movements are the main challenge in burst denoising, and our goal in this work is to enable burst denoising under large misalignments and high noise. More formally, given multiple noisy images that depict the same scene, the goal of burst denoising is to recover a noise-free target view. To solve this problem, one line of research predicts per pixel per frame kernels. Due to computational constraints, the kernels are limited in size and hence can only handle small misalignments. Another approach, named DeepRep, implements a map estimator as a deep learning network using an existing optical flow network for motion compensation. However, current methods struggle when it comes to large misalignment under high noise, and you can see mobile phone ask the user to hold still while capturing in night mode. Our main insight in this work is that the burst denoising problem can be formulated as an image synthesis problem. The difference from the denoising problem is that instead of denoising an existing image, the goal is to synthesize a new one, assuming that the input images are all clean. Recently, NERF proposed a new approach to image synthesis, which was extended by IBRNet to operate without Bayesian optimization, given a small number of input images. To adapt it to burst denoising, we build on IBRNet and make it noise-aware by adding spatial and temporal components that explicitly deal with the noise. Let's see first some results. For training and testing, we used burst dataset from previous papers. This is an example of a clean target view from the testing set. We added to the images Gaussian noise and marked some interesting areas with rectangles. Our algorithm manages to remove the majority of the noise while preserving the details. Note the area marked in the rectangles. Although the DeepRep result is slightly smoother, it yields some visible artifact and faded objects as can be seen in the rectangles. For comparison, this is our result again. The BPN network leads to severe color artifacts due to the small kernels they use. For real-world scenarios, we capture several scenes in low light using a Pixel 4 phone. This is an example of a single dark frame from the burst. After changing the brightness level, we get this noisy image. The average of the burst here illustrates the amount of displacement between the different views. In our denoised version, it is possible to spot some fine details like the reflection and the floor lines. The DeepRep result is over-smoothed, has a cartoon-like effect in some objects like the lattices and faded-out objects like the floor lines. This is our result again for comparison. The BPN method didn't cope well with the misalignments, as you can see in the ghost artifact of the white planter, for example. And now for some details about the method. The IBRNet starts with generating an array from a specific pixel and processes each 3D point separately. It first projects the 3D point to each of the other views and uses the incident pixels. Specifically, it uses the RGB values concatenated with some corresponding feature vectors. It starts by calculating the feature statistics, then one block predicts the density and another block predicts the 3D point color as a linear combination of the incident pixel colors. This framework works well given clean images, but it is not optimized for noise. I will go over some of the contributions we made to make this framework noise-aware. We empirically showed that the simple statistic cues are not sufficient in the presence of noise. To benefit from temporal knowledge also in burst denoising, we add a transformer which provides additional information on the relationship between the different views. To benefit from spatial denoising, we extend the color blending kernels to a 3x3 environment around each incident pixels. Further modification can be found in the paper. Thank you for listening. For more information, results, and code, please visit the project website.